there are various ways of looking into these different areas. One of the ways of doing that is to stimulate these different areas. That was done by Wilder Penfield originally back in the 1950s during surgery in patients. And basically, when they had a subject during surgery, basically when you're doing surgery in the brain, you can have people who are fully awake, since you don't have to anesthetize them when you're doing surgery on the brain, since there are no pain fibers. So what they could do was to stimulate these different areas of the brain. And what they would see was that when stimulating Broca's area, you would immediately prevent the people from being able to produce language. What they describe is that when immediately, so subjects were talking, they were asked to read a sentence that they, or read a text on a piece of paper, and immediately when they started stimulating, subjects would continue moving their mouth as if they were trying to talk, but they weren't able to actually produce this. Whereas when they were stimulating the sensory or the primary motor areas, they would sort of inhibit the muscle activity and prevent them from actually using the muscles in order to produce the words that they wanted to produce. This is very similar to what can also be done nowadays using repetitive TMS over these different areas. So this is a study which was published originally by Paul Jenum. He's now at Glostrup Hospital. So this is a Danish study originally. And I was actually one of the subjects for this study originally. And this is one of the most amazing things you can experience, because when you stimulate over Broca's area, what you experience is that when you're trying to just continue talking, you just lose track of what you were going to say. So you feel you can move, but the intention, the idea that you had of what you wanted to say just doesn't get out there. So you just go and nothing comes out. So it's really, really fascinating. Stimulation of Wernicke's area is somewhat a different experience, because what you do is you read a text and you can read the text, but when you get this stimulation, you know that you can see it, but you don't really get the idea of what is there. So even though you're conscious that you can see the letters, it just suddenly makes no sense to you. So it just poof, disappears from your mind, what is actually there right in front of your eyes. It's pretty fascinating, I have to say. You can also sort of image language by, in this case, it's a PET study. You can do it now also with fMRI. Basically, if you have subjects passively viewing words, you will see activation in the visual cortex. If they actually start listening to words and trying to interpret what is happening, you get activation in the auditory cortex and also in Wernicke's area. If they then have to speak the words that they're reading, you see activation in the primary cortex. But if they actually have to generate verbs, you see more activity in Broca's area and also in Wernicke's area. So you have an internal generation of thought, you could say, where these different language areas are brought into play as a network in order to generate these different verbs. So this is just a summary of what I've just been saying, how you put words into speech, essentially. So if you have some written word, you have to see it with your eyes. It has to go into the visual cortex. You have to recognize it as words, you have to put it together and end up actually being able to code that into some kind of organization of different muscles being active in order to produce that particular speech. If you're listening to words instead, it's the auditory cortex. You have to process that and again end up producing it as words. So you can follow that path through the different areas of the brain. Now, there's also quite a lot of plasticity in this, as I started out saying also, and which is also something that we have been talking about earlier on. The original finding is sort of this one, and I can't remember how much we've been talking about it already, and it may be that Mark has also been mentioning it, but this is the original finding from Sadato et al. In 1996, in which they observed that subjects who became blind before they were born, as adults, when they're reading Braille, they get activation not only in the motor cortex and in the sensory cortex, but also in the visual cortex, so that you could sort of say that they're seeing the words that they're reading. They're using the capacity that is there in the visual cortex in order to process the sensory information that they get when they're reading this Braille alphabet. Very much the same thing is seen in subjects who are deaf. So in deaf subjects, you actually see when they see words that they process it to a very large extent also in the auditory cortex. So even though they cannot they cannot hear anything, they're using that part of the cortex which they normally use for which normal people would use for processing auditory inputs. They use it now for processing visual inputs. So that there is this huge amount of plasticity in the organization of the brain. So the different sensory areas basically become functionally dedicated through experience in early childhood is the general idea.